Hello everyone, today we will start with session 2 of coordination compounds. Students are requested to drop down their names for attendance purpose. We will be starting in a while. Students are requested to drop down their names for attendance purpose. We will be starting in a while. Okay, so let's start. Now, I gave you a question that why NH2 cannot act as a chelating ligand. Why NH2 cannot act as a chelating ligand. Anyone with the answer? This question I gave you for homework. Anyone with the answer for this question? Why NH2 cannot act as a chelating ligand? What is chelation? That means formation of a ring, right? The ligands which are able to form ring tend to show chelating effect. Anyone who was able to find out the answer for this particular question? See here, particularly here if you see that NH2, let us say that it is forming a ring with the metal, right? Let us presume that it is forming a ring with the metal like this. This property is known as chelation, where a ring is formed, right? Now here if you will see that a three-membered ring is being formed, right? So three-membered ring is not stable. Three-membered ring is not stable as it involves much of strain. It involves very much strain. That is why three-membered ring is not stable. And due to the lesser stability of the three-membered ring, NH2 cannot act as a chelating ligand, right? However, if the ring expands to five-membered or six-membered, then the ring becomes stable. Five and six-membered are the most stable rings. Okay, and three-membered is the least stable ring because it involves much of strain. Now next, this you tell me, EDTA 4 minus is what? A hexadentate ligand, a chelating agent. C says both A and B, and D says none of them. Ethylene diamine tetraacetate. Ethylene diamine tetraacetate. First draw the structure. Ethylene diamine tetraacetate. This is the structure for EDTA 4 minus. Now explain what should be the answer for this particular question. Anyone with the answer? Is this ligand hexadentate? Is this ligand chelating? C says both. It is hexadentate also and it is showing chelation also. And D says none of them. That neither it is hexadentate and neither it is a chelating agent or chelating ligand. A is correct. What about B? Will it do chelation? Will it do chelation? So as it is a polydentate ligand particularly, it will show chelation also. So A is correct as it is hexadentate ligand. One site is this, second is this, third is this, fourth is this, fifth is this, and sixth site is this of donation. So it is a hexadentate ligand. And second one, it forms chelate ring also. Right? So A and B both are correct. Now we were doing the terms related to coordination compounds, right? We have completed ambidentate ligand, bidentate ligand, tetradentate, pentadentate, what is metal atom, what is central atom. Now we will see one more type of classification of ligand, that is flexidentate ligand, right? So a ligand which shows variable denticity, that is known as flexidentate. As the name suggests, flexible denticity, right? So here if you will see that in this complex, cobalt NH3 4 CO3 2 minus, this is carbonate particularly, CO3 2 minus, here it acts as a bidentate ligand, but in this complex it is acting as a monodentate ligand, right? So the ligand which can show variable denticity are known as flexidentate ligand. In some complexes it may show bidenticity, or in some complexes it may show monodenticity, or in some complexes it may show tetradenticity, depending upon the type of ligand or depending upon the number of donation of sites, right? So these types of ligands are known as flexidentate ligand. Okay, so let us see this one. So if you will see SO4 2 negative, right? So if it donates from both the oxygen, then it will be a bidentate ligand, and if it donates from only one oxygen, then it will be a monodentate ligand, right? Other examples are, for example, NO3 minus, acetate, CH3CO minus, or S2O3 2 minus. They can also act as flexidentate ligand. Examples are very much important from the examination point of view, especially from the competitive examination point of view. They may ask you such type of question that amongst these four, which one acts as a flexidentate ligand. For example, if you take NO3 minus with 3D series metal atom, particularly it acts as a monodentate ligand. It acts as a monodentate ligand. But with uranium, as the size of the metal atom increases, it also increases its denticity, right? So NO3 minus, S2O3 2 minus, CH3CO minus, SO4 2 minus, CO3 2 minus, they all are flexidentate ligand. That means they are having the ability to show different denticity in different complexes. Do not confuse it with ambidentate ligand, right? You should be clear with the definitions of flexidentate as well as ambidentate ligands. Now next is the coordination number. So coordination number is defined as the number of coordinate bonds formed by central metal atom with the ligands. That means how many number of bonds, how many number of coordinate bonds are formed by the metal with the ligand is known as coordination number. So here if you will see in platinum Cl62 minus, let us say I'll draw the structure. 4, 5, 6, right? So here how many metal ligands bond are there? 1, 2, 3, 4, 5, 6. So the coordination number of platinum would be 6, right? So in case of monodentate ligand, coordination number equals to number of ligands. For example, Cl is a monodentate ligand, right? Because it has only one site of donation. So here there are 6 Cl, that means the coordination number of platinum would be 6. In case of polydentate ligands, coordination number will be equal to number of ligands into denticity. This is important. For example, consider ethylene diamine, NH2, CH2, CH2, NH2, right? And take a arbitrary complex. Let us say I am taking COEN3, right? Where CO is the abbreviation of ethylene diamine. Okay, so one En will make two bonds with cobalt. Here if you will see cobalt, NH2, CH2, CH2 and then NH2. So here one En ligand is making two bonds with cobalt because its denticity is 2. So 3 En ligands, 3 ethylene diamine ligands will form how many bonds? 6 bonds, right? So in total how many number of metal ligand bond are there? 6 metal ligand bond are there. Therefore the coordination number of cobalt in this complex will come out to be 6. So this you have to remember that in case of monodentate ligands only, the coordination number is equal to number of ligand. But in case of polydentate ligand, that means the ligand which show denticity more than 1, coordination number will be equal to number of ligands into their denticity. For example, ethylene diamine was having a denticity of 2 because it is a bidentate ligand. So number of ligands is what? 3 and denticity of each is 2. So this will give you 6. So 6 is the coordination number of cobalt. So this way you have to find out the coordination numbers. Next you come on to the coordination sphere. This also we have discussed this before only in the first session. However, we will revise it. Right, this is known as what? The ionization sphere. The species which is outside the bracket is known as ionization sphere, right? Or it is also known as the counter ion, and the species which is in the square bracket, that is known as what? Coordination sphere. This will be known as what? FeCN6. This will be known as coordination sphere, and this will be known as what? The species which is outside the square bracket is known as what? Counter ion or ionization sphere. Okay, so basically it is known as the ionization sphere. Why? Because when you will dissolve this complex into water, this will ionize. These two will ionize particularly, right? K plus will be separated from this particular complex, and the one which will not break is known as the coordination sphere or complex, right? So because this particular potassium ionizes in the solution, therefore it is known as ionization sphere, and the species which is enclosed in brackets, it is known as coordination sphere. Now coordination polyhedron, this is important. See in for example in BA-CPR theory in chemical bonding, you must have learned that when steric number equals to 2, then it is linear. The steric number equals to 3, then it is trigonal planar. When steric number equals to 4, then it is tetrahedral, right? These all geometries we have learned, right? Based upon the number of bonds that is formed by the central atom. Similarly, here also the spatial arrangement of the ligands which are directly attached to the central atom or ion is called the coordination polyhedron. That means the ligands, the arrangement of the ligands around the central metal atom, that is known as the coordination polyhedron. For example, you can recognize that this is the octahedral geometry. So here the spatial arrangement or the coordination polyhedron is octahedron. Here it is a tetrahedral geometry. So the coordination polyhedron is tetrahedron. Here it is square planar. So the coordination polyhedron is square planar. Here it is trigonal bipyramidal because 5 ligands are associated. So the coordination polyhedron is TBP, right? And coordination number 5 particularly can have two types of geometry, square pyramidal and trigonal bipyramidal. However, the geometries we will discuss in detail afterwards. Just you need to remember that the arrangement of the ligands around the metal atom is known as what? Coordination polyhedron. For example, here if you will see, the coordination number is 6, so octahedral. Coordination number 4, so tetrahedral. Coordination number 4, it can also have square planar. So particularly in this chapter, we will be also able to distinguish that why this complex is forming tetrahedral and this particular complex is forming square planar geometry. Right? This also we will be able to distinguish afterwards in this chapter. Next is the oxidation number of central atom. Right? This is the same as we did it in redox chemistry. Right? The same concept needs to be applied, provided that you know the charge on the ligand. That is very much important, right? So here if you will see the proper definition of the oxidation number of central atom, the charge of the complex, if all the ligands are removed along with the electron pairs that are shared with the central atom, is called the oxidation number of central atom. That means the charge that will be acquired by the complex if I remove all the ligands along with their electron pairs, right? So that is known as the oxidation number of central atom. The way to calculate the oxidation number is very simple, right? It is somewhat similar to that of the redox. So here if you will see copper CN4 3 minus, right? So let us take particularly the oxidation state of or the oxidation number of copper as X, right? This we need to find out. Now Cn is having what? Cn negative, so it is having a -1 charge. So if one Cn is having 1 minus 1, so 4 Cn will be having -4, so X minus 4, and the total charge on the complex is -3, will be equal to -3. So X will be equal to what? -3 plus 4. So X will be equal to what? +1. That means copper is present in its +1 oxidation state in this particular complex, right? So this is how you can find out the oxidation number of central atom. Now next you tell me this question. See, Sham, you're talking about coordination number in polydentate ligand. So here if you will see, let us say oxalate ion, right? So this is COO minus and COO minus. Let us take, I am taking an arbitrary complex, right? Fe C2O4 I have to build up a complex, just a second. Yeah, you take this one only. Let us take this one only. Chromium C2O4 3 minus. Let us say suppose this is the complex, right? Now oxalate ion if you will take, what is oxalate ion? COO minus, COO minus. So its denticity is equal to what? 2, right? So here if I connect one oxalate, this will be connected like this. If I connect one oxalate to chromium, so it will make one ligand, one oxalate is making two metal ligand bonds, right? Why? Because its density is equal to 2. So one oxalate is making two metal ligand bonds. So 3 oxalate will make how many metal ligand bonds? 6 metal ligand bonds, right? So the coordination number will come out to be 6. You can draw it this way. Let us say O, C double bond O, then O, C double bond O. This is first oxalate, this is second oxalate, and the third one I am drawing here. So how many metal ligand bond are there? 1, then 2, then 3, then 4, then 5, and then 6. So the coordination number will come out to be 6. Right. So this is how it depends upon the denticity. For example, let us say if we are having EDTA 4 minus, EDTA 4 minus, right? Now we know it is a hexadentate ligand. It is a hexadentate ligand. For example, I am taking any arbitrary complex. Let us say it is having cobalt EDTA 3. Let us say this is some sort of complex, right? This is just a hypothetical complex I am taking, okay? So one EDTA makes, because it is hexadentate, it makes 6 metal ligand bonds. So 3 EDTA will make how many? 3 into 6, that will be equal to 18. So the coordination number will come out to be 18. Right? This way you can find out the coordination number. I hope it is clear now. Rest of the students are requested to solve this question and let me know the answer. A, B, C or D. You have to find out the coordination number and the oxidation state number of chromium. So this is K3, Cr, C2O4, 3. This is the complex. Now you tell me that what is the coordination number of chromium and what is the oxidation state number of the chromium. Anyone with the answer? Anyone with the answer for this particular question? Answer this question. Potassium, you can take it as +1, and oxalate is what? C2O4. Just now I have solved it. C2O4 2 minus. So one oxalate contains 2 minus charge. Anyone with the answer? What should be the coordination number? Coordination number and oxidation state number? I'll give you one more hint. See, K3 is what? 1K is plus 1. Right? So 3K will be plus 3. So this will become particularly plus 3, and this one will have a negative charge, that is minus 3 here. Now you tell me Cr C2O4 3 minus. Now you tell me for this complex what should be the coordination number and what should be the oxidation state of metal atom. Coordination number and oxidation state. Yes, you are correct with your answer, Sham. A is the answer. So here if you take, see, this can be written as Cr C2O4 3 minus, right? Because potassium is having plus 3 charge particularly, so the equal and opposite charge will be beared by the complex. This will be 3 minus. So this will become, see, 1 oxalate. What is the coordination number? Number of ligand into its denticity. Number of ligand into its denticity. So denticity of oxalate is 2 and number of oxalate is 3. So the coordination number will come out to be what? 6. Now you come up to the oxidation state. So this will be X for chromium. 1 oxalate is having 2 minus charge. So 3 will be having minus 6 charge equals to minus 3, the total charge. So this will become equal to what? Plus 3. So the answer is A. Sham, you are correct with the answer. Now, next is the homoleptic and the heteroleptic complexes. See, the complexes in which all the ligands are the same, all the donors are the same, that is known as what? Homoleptic complexes. In which only one kind of donor atom is there, that is known as homoleptic complexes. So here you can see that ammonia is the donor ligand only. Heteroleptic if you take, so this is the opposite, that more than one kind of donor atoms are there. So here it is nitrogen and here it is chlorine, right? So two types of donor atoms are there, that is why it is known as what? Heteroleptic complexes. So homoleptic is what? Homo means same, that means same kind of donor atoms, and heteroleptic means what? More than one kind of donor atoms. Next is labile and inert complexes. We will learn ligand substitution afterwards, but you can remember that, for example, let us take, I am taking a arbitrary complex, cobalt NH3 5 Br, let us say. This is the complex. Now I want to substitute Br with some other ligand. Let us say I have to substitute it with Cl, right? I want the complex as cobalt NH35Cl. This is how I want the complex to be. That means I am substituting Cl in place of Br. If I want to carry out that substitution, if the complexes particularly undergoes ligand substitution fast, that means it reacts fast to form this particular product, it reacts fast toward ligand substitution, then it was known as a labile complex. And when it will react slow, when the ligand substitution will be slow, that means the Br will be slowly replaced by Cl, then it is known as what? Inert complexes. The complexes which react fast are known as labile complexes, and the complexes which reacts slow, that are known as what? Inert complexes. Okay. Now this is important, effective atomic number. So this concept was particularly termed by Sidgwick, right? The formula for effective atomic number is what? Remember the formula, Z minus oxidation number of metal plus 2 into coordination number of complex. This is very much important, where Z is the atomic number of metal atom, On is the oxidation number of metal, and Cn is the coordination number of complex. So what is the significance of this effective atomic number? It tells you about the stability of the complex. It tells you about the stability of the complex. So the complex in which EAN equals to next inert gas atomic number, that will be more stable. Right? So here it is very important. See, here we have taken 2. Why we have taken 2? Because almost each ligand donates 2 electron. Almost each ligand donates 2 electron. For example, if you consider ammonia, right, it donates 2 electrons. That means in a coordinate bond, 2 electrons are donated, one at a time. In one single metal ligand bond, 2 electrons are donated. However, in case of NO, it is a 3 electron donor. So here you will write 3. Instead of 2, you will write 3 if your ligand is what? NO. Okay, this is the difference. Now let us calculate effective atomic number. For example, let us take FeCO5. So FeCO5. First, what is the atomic number of iron? 26. Minus the oxidation state. So oxidation state here is 0. Right? And then plus 2 into, what is the coordination number of iron here? 5. Because CO is a monodentate ligand. Right? So this will become 26 plus 10. That will be equal to what? 36. As CO is a neutral ligand particularly, so this will be X minus 0. There is no charge here also, so this will also be 0. So X will come out to be 0. That means the oxidation state of iron is 0. Okay. Now next we will calculate it for cobalt NH36 3+. So this will be cobalt atomic number is 27 minus oxidation state. So oxidation state you have to calculate it like this. Cobalt NH36 3+. Ammonia is also a neutral ligand. So X minus 0 equals to plus 3. So X will come out to be what? Plus 3. So this will be 27 minus 3 plus 2 into, because ammonia is a monodentate ligand, so the coordination number of metal will be 6. So this will be 2 into 6. That will be equal to what? 24 plus 12 equals to 36. Now let us calculate it for nickel carbon monoxide 4. So this will be, first you calculate the oxidation state, particularly carbon monoxide is what? Neutral ligand. So this will be X minus 0. No charge here also. So this will be 0. So X equals to 0. That means the oxidation state of metal atom equals to 0. So nickel, the atomic number is what? 28 minus 0 plus 2 into coordination number. So coordination number will be 4 because carbon monoxide is particularly what? A monodentate ligand, or carbonyl is a monodentate ligand. Instead of carbon monoxide, remember that this will be called carbonyl. Carbonyl. So this will be 2 into 4. This will become 28 plus 8. That will also be equal to 36. Again, we will calculate it for copper. First, we will calculate the oxidation state. Copper CN4 3 minus. So this will be X. Cyanide is a negatively charged ligand. So Cn minus 1. This is there, right? So this will be minus 4, because if one Cn is having 1 minus 1, so 4 Cn will be having minus 4 equals to total charge is minus 3. So this will become X equals to plus 1. So copper, the atomic number is 29 minus the oxidation state 1 plus 2 into coordination number. So coordination number here, if you will see, it is a monodentate ligand. So the coordination number will come out to be 4. So this will be 29 minus 1 plus 8. That equals to 28 plus 8, that equals to 36. So in this way you can calculate the effective atomic number. Now you calculate it for iron in K3FeCN6 and let me know the answer. What is effective atomic number for iron in K3FeCN6? Anyone for K3FeCN6? I'll help you with the oxidation state. See, again it is plus 3, potassium is plus 1, so 3 potassium will be plus 3 and the equal and opposite charge will be beared by the complex. So this will be what? FeCN6 3 minus. For this complex you have to find out the effective atomic number. Find out and let me know. Okay, Shivranjani is saying 35. Let us see. So the oxidation state here will be coming out to be X minus 6 equals to minus 3, that is equals to plus 3. So iron is having atomic number as 26, then oxidation state 3, then plus 2 into what is the coordination number here? 6, as it is a monodentate ligand. So this will be 23 plus 12, that will be equal to what? 35. Good. Shivranjani, you are correct with the answer. The effective atomic number is 35 for this. Good. Now, next is that how particularly we write formulas of coordination entities. See, so the rules are there. There are two types of coordination entities that will be we will be coming across. One is the mononuclear and one is the binuclear. Right? So this is the mononuclear where only single central metal atom is there. So here you can see that only cobalt is the metal atom. Here you can see that only iron is the metal atom. So this is a mononuclear coordination entity. Okay. Now if you consider binuclear, bi means what? 2. So that means 2 metal atoms will be there. So here 1, 2, cobalt and chromium. Here chromium and cobalt. So these are what? Binuclear coordination compounds. So if one metal atom is there, mononuclear, and if more than one is there, let us say 2 are there, so it will be binuclear coordination compound. Okay. First rule is this one, that it is a mononuclear entity while these are the binuclear entities. Now we have to particularly see the rules for writing the coordination entity formula. We are not naming them. We are not doing nomenclature here. Right? Nomenclature we will be doing in the next class. Here we are only subjected to writing the coordination entity formula. So first you have to list the central atom, that is the metal atom. First you have to identify that which one is the metal atom. Once you are done with this, now you have to arrange the ligands, right? So while arranging the ligands or writing the ligands in the coordination sphere, you have to list them in alphabetical order. This is very important. For example, let us say that I am taking amine and I am taking aqua. So the ligand name of water is what? Aqua. We do not write it as water, we write it as aqua. And here it is amine, that is ammonia, if you will take NH3, right? So which comes alphabetically first? A and A is the same. So move on to the next letter, that is Q, and here it is M. So M comes first, then that of Q. So therefore, while listing the ligands in the complex, we will write amine first and then aqua at the second. That means, let us say we are having a complex containing both amine and aqua. So I will write NH3 first and then I will write down water or aqua. Okay, so you have to list them in alphabetical order particularly. Okay. Polydentate ligand, if you consider, they are also listed alphabetically, and the one which are abbreviated, for example, if you take ethylene diamine, so we abbreviate it as EN. So while arranging alphabetically, you will consider what? E, right? You have to consider E for that. Okay. Next is the formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. That is very much important. See, once you are writing down with the metal, then you have listed down the ligands, let us say alphabetical wise, right? Now you have to enclose them in square brackets. Okay. Now, when ligands are polyatomic, their formulas are enclosed in parentheses. This is very important. For example, let us say I am having 5 ammonia, right? So I will enclose them in curly brackets, what you call, not curly brackets, circular brackets, or you call it parentheses, right? These parentheses, and then you will write down the number. Okay. Here also ligand abbreviations are also enclosed in parentheses. For example, let us say I am taking 4-ethylene diamine. So you will write it as EN4. EN4. You will enclose it in parentheses. I'll again repeat. First you have to list the central atom or the metal atom. Let us say I am having here Fe. Okay. Then the ligands are then listed in alphabetical order. For example, let us say I am having NH3 and water. So amine and aqua, amine will come first in the dictionary. So I will write down NH3 first and then I will write down water secondly, because I have to arrange them in the alphabetical order. And then you have to enclose the entire formula in the square brackets. And for example, let us say that I am having 5 ammonia, then you will enclose it in parentheses and outside it you will write the subscript as the number in which it is present. Okay. And if you are taking polydentate ligands, then also you have to take the alphabetical order of the ligands. Okay. Even if you are having abbreviations, for example, ethylene diamine, you are having EN, or you are having TN, or you are having PN, right? So these also you have to arrange them in alphabetical order and then you have to write down the whole formula. This is very important, that there should be no space between the ligand and the metal within the coordination sphere. Here you can see that there is no space between the ligand and the metal atom. Okay. Now, when the formula of a charged coordination entity is to be written without that of the counter ion, for example, let us say some counter ion is not present. So the entire charge of this complex, you will write it on the right hand superscript side, right? This is the charge of the whole complex will be written as superscript on the right hand side, right? For example, if you are having 3 minus as the charge, so you will write it on at the right, as the right hand superscript of this formula. And then if you are having 3 plus, let us say, of the whole complex, then you will write 3 plus on the right superscript, and this is very important that first you will write the magnitude and then you will write the sign. For example, it is 3 plus or 3 minus. Okay. Now next, the charge of the cation is balanced by the charge of anions. This is very important. For example, let us say that I am having K3 FeCN6. Now I know that potassium is what? Plus 1. So 3 potassium will be plus 3. So if it is having plus 3, then the other complex particularly will have minus 3. Right? Equal and opposite charges will be there. This is very important. So now the next one is very important, that you have to write down cation first and then you have to write down anion. For example, here you will see that potassium is the cation and this whole complex is the anion. So you are writing potassium first and anion afterwards. Now this is a positively charged complex while Cl is negatively charged. So therefore you are writing cation first and then anion afterwards. For binuclear compounds also, you will write cation first and anion afterwards. Right? Here also this will be the cation and this will be the anion. Okay. Here you can find out the charge also. For example, let us say cobalt I am having 3 plus. So this will be having minus 3. Right. Here if I am having particularly plus 3, then it will be here as minus 3. So you are writing what? Cation first, anion afterwards. Right? Here the charges are not mentioned as 3 plus and 3 minus because cation and anion are written down simultaneously. Right? While in the case of ionization sphere, if you are having, let us say, K4 FeCN6, so you can also write it as 4K plus FeCN6 and then 4 minus, equal and opposite charge, plus 4 minus 4. Okay, always remember this, that you have to, in binuclear compounds also, you are having cation first and then anion second. So that's all for today. We will be dealing with the nomenclature part in the next session. Till then, happy learning to all.